All right, hi everybody, and this is going to be a solution that you guys asked for, which was this problem 75 from chapter 4 on relative velocities, basically. So it basically tells us a boat can be rowed at 8 kilometers per hour in still water. Well, let's just start there. 8 kilometers per hour in still water. So that means that's the velocity of the boat with respect to the water. So I highly recommend using this notation. It helps a lot. Then it asks me how much time is required to row 1.5 kilometers downstream in a river moving at 3 kilometers per hour relative to the shore. So that's the velocity of the water with respect to the shore. Often I write with respect to the earth, but because they're giving me shore, I'll say shore. Okay, and it's going 1.5 kilometers downstream. 1.5 kilometers downstream. So I'm going to call that delta x. All right, so I'll cut to my diagram that I already drew to save time. I got my boat. My boat is moving to the right with its velocity relative to the water. So it's the velocity of the boat with respect to the water. I've also got the velocity of the water with respect to the shore. If they're talking about downstream, that means the velocity of the boat is moving along with the velocity of the water. So you can, and then I also wrote the distance, delta x, down here. So it's the 1.5 kilometers the boat's going to travel. And so we can even mark that the problem's going to start here and it's going to end here. And so I've got my knowns here. My velocity of the boat with respect to the water is 8 kilometers per hour. The velocity of the water with respect to the shore is 3 kilometers per hour. And the velocity, and the distance that the boat is going to be traveling is 1.5 kilometers. And we're trying to find out what's the time. So to do this, I'm going to use that idea of the equation we've been using for relative motion. So I'm looking for the velocity of the boat with respect to the water. And so I can use my knowns to try and write out what would the velocity of the boat be with, the boat with respect to the shore. What would the velocity of the boat be with respect to the shore? Well, that's just going to be the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. And I know I did this right because I often look at these W's. I often think of them as being sandwiched in between right here, and then the W's cancel each other out, and I get the boat with respect to the shore as my answer there. So as long as I fit that form, I should be able to get this here. So, okay, let's see what that looks like. So let's see. I have the velocity of the boat with respect to the shore. Now the velocity of the boat with respect to the water, already written, already there. So it's just going to be 8 kilometers per hour plus the velocity of the water with respect to the shore. That's that. So that's 3 kilometers per hour. And I get the velocity of the boat with respect to the shore is going to be 11 kilometers per hour. Now, am I done? Is that my answer? No, because they want me to find out what's the time. So in this case, I'll use the fact that the definition of any velocity, so let's kind of use this, the definition of any velocity is going to be the displacement over the time. So doing a bit of algebraic manipulation, I can get that the displacement over the velocity of the boat with respect to the shore is going to be the time. So my displacement is 1.5 kilometers. And my velocity of the boat with respect to the shore is what I just found here, 11 kilometers per hour. And so kilometers cancel out. I'm going to get this in hours. So I get that my displacement is 1.5 divided by 11. .136 hours. And then you can convert that to minutes, and that'll give it to you in minutes, but I'm not going to do that for time's sake, so you can convert to minutes. So now for part B. Part B's setup is, well, let's see what they're even asking. So it basically says how much time is required for the return trip. So basically now it's the exact same setup. It's the exact same setup. So same setup as A, except now my initial moment is at the end here, and then my final moment is at the beginning here. So I'm starting here, I'm ending here. So in other words, my displacement is going to be negative, and the boat's velocity is going to be negative. So now the boat is starting here, so the velocity is going to switch this way, and then my displacement is going from here to here. So that would be my new displacement. Okay, so basically what that means is everything is the same except the velocity of the boat with respect to the water is now -8 kilometers per hour. And my displacement is now -1.5 kilometers. And I'm really just going to use that same equation, that the velocity of the boat with respect to the shore, that's what we're looking for, is the velocity of the boat with respect to the water, plus the velocity of the water with respect to the shore. Plugging everything in, I get the velocity of the boat with respect to the shore is equal to, now I'm plugging in this new velocity of the boat with respect to the water, because the boat's now moving to the left. It's 8 kilometers per hour. Forego units for simplification, plus the velocity of the water with respect to the shore is still moving to the right at 3 kilometers per hour. That comes from part A's information here. And then I get a new velocity, which hopefully makes sense because the boat's going against the current, of -5 kilometers per hour. And so again, taking that and using the definition of a velocity of anything is the displacement divided by the change in time. So that basically means that my change in time here is going to equal the displacement divided by the velocity, which equals the change in time. My displacement is -1.5 kilometers. My velocity is the velocity of the boat with respect to the water, which is -5 kilometers per hour. The negatives cancel out, the kilometers cancel out, and I get my new time, which, think about that intuitively, it should be longer, right? So I get 1.5 divided by 5, 0.3 hours, and of course that is longer than 0.136 hours. So there you go, there's part B. Yay! All right, moving on to part C here, which I think we get a little change of pace now. In what direction, so it's saying in what direction must the boat be aimed to row straight across the river? Suppose the river is 0.8 kilometers wide. Okay, let's go back. Well, I'll just redraw it. So basically now we got some shore here. Shore, and then we got some shore here, shore, and it's saying, well, the river is still going to be the velocity of the water with respect to the shore is still pointing this way at the same speed. That hasn't changed. 3 kilometers per hour. So I can write that in a, so velocity of the water with respect to the shore is still 3 kilometers per hour. But now the boat is going to be going this way. But you know, if I just go this way, if this is the velocity of the boat with respect to the water here, like this, The velocity of the boat with respect to the shore is going to be moved along with the water and just kind of make its way that way. What this problem is basically asking us to do is, what is the velocity? What angle do we have to? Do we have to aim our velocity at in order to just have the boat go straight across? So no going this way. Let's make this a little bit bigger to make it a little more proportional, something like that. So as you can probably guess, the velocity in which we'd have to point, well, let's add up these vectors. So if we added up these vectors like this would be the total velocity that the boat would travel. And basically I want to make it so that the velocity angle here, I would want it to be going though this way, so that the velocity of the boat, the x component of the boat's velocity here will cancel out with the velocity of the shore, the velocity that the water, the velocity that the water is exerting over there. So if I do that, I'll be able to find this. So I'm going to move these over here, back over here, and I'm going to break this thing up into its components. Let's see, what would be the best way? So here's going to be my velocity of the boat with respect to the water. This thing, it's going to go like this. But then I'm going to get some component going up, and then some component going to the left. So this would be the velocity of the boat with respect to the water along x. And let's make this red. This would be the velocity of the boat with respect to the water along y. And now I get a choice of angle. It doesn't matter. I could choose this angle. I could choose this angle. It doesn't matter as long as you explain where you're coming from. I think the book uses this, but in my answer I used this, which is okay. So that's what I'm going to use there. And so yeah, here we go. Let's see. The velocity of the boat with respect to the water is still 8 kilometers per hour. So I know it's going at an angle there, but we'll take into account direction when we split this vector up into its components. And now we're looking for the angle. So we're looking for the angle, theta. And let's see, I know this is 8 kilometers per hour. So I'm looking for, let's see, I can find the angle because I know, let's write VBWX, so I can use trig here, and I can use trig, so if I had like my VBY over there, I can use trig and basically say, well, cosine of my angle is going to give me VBWX over the magnitude of my velocity VBW. And because there's multiple directions, let's just say that the magnitude. So say the magnitude. And so multiply both sides by VBW. So VBW, the magnitude of that is going to be cosine of my angle. Oh, I don't really need to do that. Well, let's do it just to simplify, because I know what my last steps are going to be, but it's okay. We can just do it again. So VBWX. And now, so let's just plug in some numbers for funsies. So I know this is 8 cosine theta equals VBWX. What do I want VBWX to be? Well, I want VBWX to be the opposite of whatever VWS is. So the velocity I want of my boat with respect in the x direction, I want it such that it cancels out the velocity that the water is pushing to the right with respect to the shore. And the velocity is moving to the right with respect to the shore at a velocity of 3 kilometers per hour. So I basically want VBWX to be -3 kilometers per hour. If you were doing this on a problem or on an exam, I would want to know why you would want this to be the case. So, well, I'll just write it down. So, VBWX must equal the opposite of VWS in order to cancel VWS. So I'm explaining why I'm plugging that in as 3 kilometers per hour, or give me an equation, show me, explain to me that you know what you're doing and why you're doing what you're doing. So this is 3 right here. And now I can solve for my angle. So it's going to be cosine of theta equals -3/8. I'm going to take the inverse cosine on both sides. It's going to give me the inverse cosine of -3/8. And so that gives me that the angle I need to move at is the inverse cosine of -3 divided by 8. Oop. Got an imaginary number. That's not good. There we go. 112 degrees. So I get 112 degrees right there. Now, what is that 112 degrees? That's always with respect. Anytime you do something in your calculator, it calculates, assuming you're talking about with respect to the positive x-axis. So my angle here, well, even though I have it called here, it's the calculator doesn't know that that's what I'm using as my point. So it's saying from here to here, this they're telling me is 112 degrees. So if I wanted this angle that I drew and made, I would say, well, that's going to be 180, the total straight line, minus 112. So it's going to be, let's see, that's 8, 7, 68 degrees. So it's going to be 68 degrees. Or I could say 68 degrees above the negative x-axis. So yeah, as long as you got a diagram and you're explicit about what angle you're talking about and where, I mean, you got the right idea. So yeah, all right. There's that one. It doesn't matter. I'd choose this one. Fine. Or you could choose this one. It just yeah. Okay. Next one. So it says, suppose the river is 0.8 kilometers wide. What is the velocity of the boat with respect to the Earth, and how much time is required to get to the opposite shore? Okay. So let's redraw it again just to make things a little simpler here. So for part D, got my shore, and I got my shore here, got my boat, boop, 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 boop. And then I got the velocity of the water with respect to the shore going that way. But now we're saying that the boat is moving this way. So here's the velocity of the boat with respect to the water. And as we said, there's a, I'm going to use blue, okay. This is the velocity of the boat with respect to the water along x. And then this is the velocity of the boat with respect to the water along y. So you can see if you were an observer standing on the shore, basically this component would cancel out with the water. So you wouldn't see any of that velocity. Really, you would just see the boat now moving straight up in that direction. So what's the velocity of the boat with respect to the, what's the velocity of the boat with respect to the Earth? Or with respect to the shore? Well, that's just going to be equal to the velocity of the boat with respect to the water along y. So all I need to do is find that. So once again, I found out this angle here, theta, is 68 degrees. And again, this velocity along y, you can think about it as like being right here as well. It's the same thing. As long as the vector points in the same direction and has the same amount, it's the same vector. So I really just need to do find out the components here. So let's see, I'll use sine. Sine of theta is equal to the velocity. Let's use it all in red because we're all working around there. So is the velocity of the boat with respect to the water along y divided by the velocity of the boat with respect to the water, the magnitude of that. So that means that the velocity of the boat with respect to the water, the magnitude, multiplied by sine of my angle is going to give me VBWY, which, as we just said, is basically going to give me the velocity of the boat with respect to the shore. And I can plug that in. Velocity of the boat with respect to the water is 8 sine of 68 equals the velocity of the boat with respect to y, which is the velocity of the boat with respect to the shore. So it's going to be 8 sine of 68. And I should say this is all going to give me magnitudes, though. I'm going to put in the direction at the end. So 8 times sine of 68, I'm getting 7.4. So just making sure that's right. Okay, so 7.4 is my velocity of the boat with respect to y, and that's the magnitude of the velocity of the boat with respect to the shore. But just to get direction, that's going to be 7.4. So units or meters per second, and then we could say in the y-hat direction it'd be positive because the boat's going directly up and to the right. So or you can use, what is it, j-hat. You can use j-hat if you want. You can use bracket notation. Anything that represents that, that'll be good. And that's the velocity of the boat with respect to the shore right there. Although, is that the answer, or are they asking for the time? What is the velocity of the boat with respect to the earth? Got that. And how much time is required to get to the opposite shore? So they want the time as well. My goodness. This problem's bossy. So again, we can use that definition of velocity. So any velocity is equal to the displacement over time. Solving for time, we're going to get that the displacement, and if you guys want to, we can call it delta y. And I'll call it delta x. No, let's call it delta y because it's different. I don't want to confuse. So we use delta y, which we did not label. So we want to make sure we label that. That's the distance from here to here. That I'm going to call delta y. And delta y has a value of 0.8 kilometers. All right. So it's going to be, going back to here, definition of a velocity, average velocity. So it's going to be delta y divided by the velocity here, which is the velocity of the boat with respect to the shore. And that's going to equal the time. So delta y, that is 0.8 kilometers divided by velocity of the boat with respect to the shore, so it's 7.4. Oops. Ooh, meters per second. Ooh, that ain't right. Kilometers per hour. Units, they're your friend. So I caught my mistake because I used units. Kilometers cancel out. We get hours left over. So I can go 0.8 0.8 divided by 7.4, and we get 0.108. So my time is 0.108 hours, and that's my answer there. You can convert it to minutes if you like. That's fine. And then the last one, I hope, is part E. Suppose instead the boat is aimed straight across the river, so it's just going boom, just using all of its velocity to go straight. How much time is required to get across, and how far downstream is the boat when it reaches the opposite shore? So if we just wanted to go full force and say all of our velocity is going to go towards getting to the shore, we'll get there in a shorter amount of time, but the problem is because the river is also pushing that way, the boat's going to end up moving somewhere over there to the right. So, okay, how much time is required to get across and how far downstream is the boat when it reaches the opposite shore? All right, so this is part E. Again, I'm going to draw my shore. There my shore. It's a crappy looking shore, but, you know, deal with it. I make myself laugh. So there we go. There we go. We got that. Now the velocity of the boat's going completely this way. So it's going, whoa, sorry about that. So velocity of the boat with respect, well, this is with respect to the shore, is now going to be, that's not the velocity of the boat with respect to the shore. It's the velocity of the boat with respect to the water is 8 kilometers per hour. You still got the velocity of the water going this way. Make that a little bigger based off my, and this would be the velocity of the water with respect to the shore. All right, so even though the velocity of the boat with respect to the water is going to be added to the velocity of the boat with respect to the shore, the velocity, the velocity of the water with respect to the shore, perpendicular vectors are independent of one another. These two vectors, this and this, are independent of one another. So whatever happens in this direction is not going to affect what happens in this direction. So whatever happens in the y hat direction is not going to change what happens in the x hat direction and vice versa. So to find out how much time it's going to take, I know this distance from here to here, delta y, is 0.8 kilometers. So I can use, again, the velocity of the water, I just want to make sure I get this right, 3 kilometers per hour. I think that's right. Yeah, 3 kilometers per hour. So I can use, again, to start with here, we're going to start with, again, this definition of velocity. The velocity of anything is equal to the displacement. We use delta y divided by the change in time. So isolating delta t, that's going to be delta y over the velocity of the boat with respect to the water is going to equal, delta y is 0.8 kilometers. The velocity of the boat with respect to the water is 8 kilometers per hour. And so, it's equal to delta t. And so that gives me that the time now is, I know this is an easy calculation, but I'm so reliant on my calculator. 0.8 divided by 8.1. Yep, that's what I thought. It's going to be 0.1 hours. You can convert that to minutes or whatever you want. So that's the amount of time it would take. But the question they also asked is, how far away is the boat going to be? Because, like we said, the boat is actually going to travel. Let's just use this. So we can use this. The boat's going to be here, and it's actually going to travel this way until it eventually ends up like here because of this vector. Because the water is pushing it to the right, it's going to travel in the path that I just showed you. So the question is, from here to here, how far did the boat travel in the x direction? So it's a good thing I used delta y then in this case, because hopefully that then doesn't get you confused with the amount that it travels in the x direction. So you could do things like add up the velocities again and figure out, what the figure out what the magnitude of the velocity is and play around with it there. But I'm going to use again the fact that perpendicular vectors are independent of one another. The only thing that they share, similar to a projectile, is the time it takes for the boat to get from one end of the shore to the other is the same amount of time it's going to take for the boat to get from here to here, this x part. So if that's true, and I know the velocity that the boat's going to travel in the horizontal direction is the velocity that the water is going to take it, so it's going to be 3 kilometers per hour. So I know that the velocity of the boat, which is the water with respect to the shore, is going to be the velocity of the boat with respect to the shore in the x direction, and that's going to equal, so say the magnitude here, and that's going to equal 3 kilometers per hour. And I also know that the displacement, well, I don't know the displacement, so I'm going to look for, but I do know the time. It's 0.1 hours. And again, I can use the definition of velocity. So all this stuff I'm going to use over here, because the definition of velocity is equal to the displacement over the change in time. So that basically tells me that the displacement over the velocity, that's going to equal my change. I'm not looking for the, I'm isolating displacement, so it's going to give me the velocity multiplied by the change in time is going to give me the displacement. So what's my velocity? It's 3 meters per second multiplied by 0.1, and that gives me a displacement of 0.3 kilometers. And there we go. So definitely a challenging problem, something you had to think about. Notice I not only set up everything showing my equation and my knowns and unknowns and things like that, but I drew a picture for just about every single one of these. Pictures are so helpful. Picture, and then the only one was B. I didn't make a picture because really it was just the same setup. I just changed the directions. So hopefully that helped you. Just kind of learning, looking at my logic as to why I did what I did. If you still have questions, please don't hesitate to come see me in class. But yeah, hopefully that helped you, and I'll see you guys tomorrow. All right, bye.